Welcome to the course on two-dimensional signal processing, principles and practices. In this course, we would be learning two-dimensional signal processing and its concepts and the signal processing. How do we make it useful in the real world scenarios? Also, the practices which will be implementing them on real-time devices would also be learned in this course. So when we start with the signals of this, particularly the signal is a set of data or the information. So we can collect this data in a regular interval, or it can be a irregular interval as well. So it will be depending on some variable, that is, it can be a time variable or it can be a space variable. So it depends on that. It could be function of variable. The data is not only the points or the amplitudes or the signals what you get, and it can be an information as well. So this information, for example, it can be a number of cloudy days in a month, or it can be a number of cars which are crossing the bridge in a particular duration of time or in one day. So these are the few examples, and it is basically a set of data which you collect in the real world scenario. So this signal is function of independent variables. This variable, as I said, that could be of time or it can be a space also. So if you see the examples of these signals, now one is could be that ECG signal, electrocardiography, which records the electrical activity of the heart. So it is actually the function of time which the electrical activity is recorded. That is again a one-dimensional signal. So if we take electroencephalogram, EEG, the brain electrical activity which could be recorded in different channels using the EEG devices. So this could be another signal. This is not only one channel. We'll place multiple electrodes on the skull, and then we record the signal from the EEG device. Also the seismic signal, if you take the earthquake, the seismograms record the seismic signals, which is also a function of time. And we'll see the signal example, the plot of this, how this signal look like. Also the speech signal can be recorded, and that can be viewed as a signal or a data or the information which is contained in the signal. It's also a 1D signal. And the music or the sound that which we hear, and there's also a signal. But if we take images, the images would be of a two-dimensional. So it will have two independent variables. And if we take this signal, that signal can be generated with a single source, or yes, a speech, suppose a vocal tract of my speech, that is from the single source, that's a scalar signal. Or the multiple sources, it can be from the different channels you get. So that will be a multiple source signal. So a signal can be a scalar or a vector. So if we generate it from the scalar, that is a single source one, and it is going to be a vector signal if it is of a multi-source. The 1D signal, as we say, the dimension of the signal is said only when how many independent variables involved in the data or the information. So if you take only one independent variable, that's the data or the information is depending on only one independent variable, that's going to be a 1D signal. So it's a function of single independent variable. So we can have the 2D signal similarly, that it will be function of data, the information or the amplitude is depending on two independent variables. It varies with respect to two independent variables, then it is going to be a two-dimensional signal. So the same thing can be extended to ND as well. So if we have the n independent variables, that could be an n-dimensional signal. So it's a function of, obviously a function of n independent variables, the ND signal. So 3D will be of three independent variables it will have. So it's a three-dimensional signal. So if we take an example or the picture of this showing the ECG signal. So ECG signal, which is the x-axis as the time, as well as this amplitude is shown over here. It is in the millivolts. It's a very small amplitude. So to process it, we will amplify always and do the signal processing. So in this case, that if you can see the PQRST pattern, which is repeating over the electrical activity of the heart. This is obviously a 1D signal, which is the amplitude is a function of time, and the PQRST things, this atrial defibrillation and ventricle defibrillation can be understood from the bio details of it. So we've just talked about the signal, how this data is recorded in using the ECG recorder, and how this ECG signal is going to be processed for. And for example, if this ECG signal, when you record it with the ECG recorder, the power line interference can occur, and that power line interference can be removed by the filter design, or the 50 hertz power line interference can be easily removed using the filter 50 hertz if it is interrupted or the corrupted with the power line interference. Or this baseline itself, you can see this baseline itself is not straight. Actually, it's not a straight line. It can wander. So if you take the ambulatory ECG, so the patient is taken in for their ambulatory care, then when they travel, they record the ECG, and you can see the baseline wander. That is a very small baseline, which is the frequency you can observe in the base also. So that could also be removed for correct identification or the diagnosis of the ECG pattern. And so this is one-dimensional signal. So the processing involves, for example, the interference removal and the baseline wander removal, and so on. So if we take the speech signal, for example, this is also an 1D signal. The speech is recorded here, and usually the speech signal is taken with the samples. So the sample can be plotted with respect to this here, what are the number of the amplitudes, what is the amplitude here. And this is also an one-dimensional signal. You can see the speech signal will have some periodicity in it. It means it's aperiodic, but still you have the quasi-periodic signal. That means a vocal and the consonants needs to be understood from the speech signal. So if you can see this, like, though it is an aperiodic signal, you can see the quasi-periodic pattern in each of the consonant we pronounce, or the letters, some of them we pronounce would be having the periodicity in it. So it's quasi-periodic signal. And if we take an example of a music signal, so it's a music signal, also again it can have an instrument playing for it. So the instrument sound and the voice of a person, the singer, will be mixed together. So it can be a voiced signal, a piece of voice signal, and a piece of unvoiced signal. So the instrument alone can also be a music signal. The instrument sound can also be a particular unvoiced frames we can have. So the music signal contains this voiced and unvoiced pattern of it. So this is a piece of music which is showing the amplitude and the time, and the amplitude is depending on the time only. This is 1D again. So for a seismic signal, suppose we take the seismogram records it, so the ground acceleration is recorded by the seismograms. So for the very first waveform, that is very silent before that, and then after that the first primary wave comes. So that amplitude is very small here, and then the secondary wave comes into the little higher amplitude after a time. The secondary wave comes later here, and then the surface wave, the surface wave is plotted over here from the seismogram. So this portion is called this surface wave. So you can see the three types of patterns available in each seismic signal. So the P wave, S wave, and then surface wave. So these waves are processed in the signal processing, the seismic signal processing, to identify or to design a warning system. Can we interpret something from the primary wave, or can we interpret something from the secondary wave? So these waves needs to be analyzed, so whether it is going to be a big earthquake or not. So these are the research which would be helpful to design a warning system in case of seismic signal. So there are three portions of it. Still, these three of them are depending on time. So that is one-dimensional signal. And if we take the images, so an image which is different from the ones which we had already discussed, that is the two of them, 2-3 examples where this is two-dimensional, that one isn't one-dimensional signal. So the function of x and y. So what is x and y? And this x and y are the spatial coordinates. So like time, what we had here, this x and y are the independent variables. So the f of x comma y, this represents the amplitude or the intensity of the picture or the image. So if we take an example of this picture, this is a grayscale image, and then this is a colored one. So we can have the pixel has some value. So if you take, this is x and this is y. for example. It can be x and y. So this x, y, each of them will have a intensity value, the amplitude value here. Okay. And then similarly each row, or you can put it in that each column as well. So these values, or the intensity values, are depending on x and y. So the x00 at this point, it has some intensity value, x0, and then y1 it has some other intensity value, and x1 and y1 it has another intensity value. So if it is a digital image, then it is good for a 3-bit image. So your 3-bit image will have 0 to 7 intensity pixels. That means 0, 0, 0, and then 0, 0, 1, and 0, 0, 1, 0, and then 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So 7 values will be occupying the whole picture if it is a 3-bit image. Okay, so this is the digital image. So these intensity values, this is 0, 0, 0, 0, 1 or anything, that is depending on this x and y. It can be in this place where x is 1 and y is 1, or x is 2 and y is 2. So in that fashion, so these intensities are occupied in the pixel, that is called the pixel values. The pixel intensity, we call it the grayscale or the colored image. So we're going to see what is the grayscale and the colored images. So image is a 2-dimensional signal. Now, if we talk about the images further, that one, if it is a black and white image or a grayscale image, so if the first one which I have seen in the previous case, that has one sample per point. So if you have the for x equal to x and y equal to 0, 0 or 0, 1, it will have only one value, one sample point in that position. That is one sample per point. Whereas in the RGB images, the colored ones, so RGB, what we mean is red, green and blue. In those images, it have this 3 samples per point. So three values are there in a single position, that is x and y. If you take x and y, is if it is going to be a 3-bit image or 8-bit image. So for example, in this point, if it is grayscale, you have only one value, and if this is going to be a 3 samples per point for RGB. So RGB, it will have 3 values in the same point. So that's when we call it one for R, one for G, and one for B. So these 3 of them contributing to the red, green and blue intensities. So that is 3 samples per point. So normally the colored images, what we deal with is other 3 sample point. So when we want to process it, whether we want to process only red channel or green channel or the blue channel, depends on the information it has, depends on the information what we would like to extract from it. So we would process that particular channel for getting the information. So this image can also have 4 samples per point, that is RGB, the red, green and blue, 3 samples and one for each, and alpha, there is another quantity here which is defining the opacity, how vivid the image is. So if you see this picture, this is a grayscale image, as we said, 1 sample per point, and then the RGB, which has the 3 samples per point, this is the one, and the third one, which here shown here, is having the RGB as well as it shows the alpha parameter, which is showing the vivid. This is like vivid, or how the vividness of the image would be. So that is another parameter which is defining the image property also. So when we talk about the images, that would be a grayscale, or it can be RGB, or it can be a 4 sample per point RGB plus alpha opacity. So now we take the video signal. So video is what dimensional here? So the 3-dimensional with 3 independent variables is the video signal. So the image we saw there are 2-dimensional, x and y, 2 independent variables, and the intensity at a particular position is depending on x and y. So now here, what happened to this video signal? So video is a set of frames of images. So one frame and the next frame and the third frame and the fourth frame when we record the video. So we keep accumulating the frames at a certain rate. So what frame rate your camera has. So when you capture the images or the video, that here, so if it is a 3D signal, it is the x and y, each image will have x and y, 2 independent variables, and its intensity pixels, and that frame is taken at a particular rate. That is the third independent variable, t, is involved in the video signal. So two spatial variables, x and y, that is f of x comma y, as we have seen in the images, and the third one is the time t, which is at what frame rate that image is taken. So that is the third quantity. So in a video, so you can see this bubble which is moving over. So what is the rate at which this frame is going to be visible, or it is recorded? So that's the third one. So video signal is a 3D signal which has x and y as two independent variables, and t is the third independent variable, and as of course each x y there is an intensity involved in it. So now we take the classification, generally how these 1D signals are classified, and we will get back to the 2D signal later after understanding this 1D signals. So this can be broadly classified into continuous and discrete signal. So when we take the signal, the set of data or the information can be classified or categorized into two. The first one is continuous in time, and the second one is the discrete in time. So the time independent variable, the data which is function of the time or the independent variable, it is continuous in time. Is it defined every instant of time, or it is defined only a certain instant of time? So depends on that. This can be two categories. One is continuous in time, another one is discrete in time. So based on continuous and discrete, so we can further classify this into another two categories. If it is continuous in time, okay, so it is defined in all instant of time, the data. And what is the data is going to be? Data is continuous, the data is actually discrete. So that it is going to be continuous in amplitude. That amplitude is even take the real values, or it can take only integer values. So this is depends on that. You can classify this again to the continuous in amplitude and discrete in amplitude. So again, discrete in time, which is defined at a certain intervals of time, that is t is going to be a integer here. And what about the amplitude? Amplitude is continuous. Can it take real values, or it can take only that integer values? So depends on that. This can be four categories. So the continuous and discrete signals can be again further classified into two. So continuous in time and continuous in amplitude, that is one category. Continuous in time and discrete in amplitude, that's another category. And discrete in time, which is continuous in amplitude, discrete in time, and discrete in amplitude. So we could have these four of them used in all the signal processing and algorithms. So if you have these continuous in time and continuous in amplitude, you would be using some of the algorithms. If it is discrete in time and discrete in amplitude, so you would prefer to use some other type of algorithms. We'll see them one by one. Now, then the continuous and discrete signal, as we said, that first category is called CTCA, that is continuous in time, continuous in amplitude, and the continuous in time, discrete in amplitude. So this is second category, and third one is discrete in time and continuous in amplitude, that is DTCA, and discrete in time, discrete in amplitude, DTDA. So these are the four categories where these signals we can see in our signal processing. So we would like to give the example here, that is, we'll take one signal x of t, which is 1.5 cos t plus 0.8 cos 2.5 t. So this is a continuous in time and continuous in amplitude signal. If we plot it, what we get, the signal is this. So whereas the time, that is the independent variable, and x of t, which is function of t, this is a 1D signal, and continuous in time and continuous, it is defined, this amplitude is defined every instant of time, and x of t is also there is no gap in between the data, that is, it is very continuous. It can take all real values of it. So if you keep increasing the t values and substitute over here and get this plot, that is continuous in time, continuous in amplitude. So real world, if you capture any signal through the sensors or anything, that going to be CTCA, that is continuous in time and continuous in amplitude. But when we sample this, actually when we sample this signal, that going to be the discrete in time and continuous in amplitude. So apply the sampling theorem, or Shannon's sampling theorem, which says that the sampling frequency should be at least twice the maximum frequency of this particular signal which you are sampling. So identify or find out the maximum frequency of this signal and choose the sampling frequency and chop this signal using that sample time. So that is going to be between this time, there is a time t involved. So I chop this signal over here and here and here at a regular interval. So that is called uniform sampling. So I chopped it and collected this data and plotted it with respect to what time it is available. So it's not the data is not defined in between one and for zeroth sample and one sample and second sample. So this is only defined at n is at a certain value, that is an integer value. So 0, 1 to n is 0, 1, 2, 3, 4, 5, 6, 7 and so on. Those values, what is the amplitude, it is known. Still this amplitude is not integer, it is going to be a real number. So it can be a 2.3 or 1.3 or 1.8 and so on. So this signal is called the discrete in time because the time can take only the integer values, and continuous in amplitude where you have the real values as well. So this signal is just sampled with the appropriate sampling frequency, the maximum frequency of it, and is identified, and at least two times it is fixed the sampling frequency, then we get the samples like this. This is discrete in time and continuous in amplitude. After that, we take this signal, the discrete in time and continuous in amplitude, and we quantize it, in the sense we make this real values to make only integer. The closer integer values are identified, that is in the quantization process. So if it is 2 here, supposing this is this signal, the sequence, what we call it here, this sequences are supposing 1.8, and again this, if you see, this is round off to 2. For example, if suppose this is 2, so 2, and then the next sample is supposing 1, and this is lower than that, suppose it is 0.5 or 0.4, and this is the nearest integer is found, and then it is made 0, 0. So these samples you can see. So likewise, the nearest integer of this particular sample is identified to round off and make this quantization. So this signal is now can, if you see the time, that is defined in integer values only n, and whereas the amplitude also 2, 1, 0, so integer values. So this particular signal is discrete in time and discrete in amplitude. So where we get this type of signal? Okay, so we'll see in the examples. And continuous in time, continuous in amplitude, discrete in time, continuous in amplitude, discrete in time, discrete in amplitude. So 3 categories are done. So now where is the 4th category, which is the continuous in time, discrete in amplitude? So we'll see this one, that is you can join these points, actually the 1, 2, 0, 1, 2 integer values for, and hold it for a while and then make it continuous. Okay, so that's the signal here. The time is continuous and discrete, still the amplitude is discrete. So that means discrete amplitude can take only integer value, but time is continuous. So if you take this, suppose this is 2 and 1, there is a line drawn between that, so it is holding that value. For 1 and 0, similarly is -1 and 0, so and so on. So these values are known for the time which is continuous. Okay, so the 4th category is continuous in time and discrete in amplitude. So where we can see these 4 types of signals when we process a signal or acquire a signal and then or transmit a signal and so on. So if we'll take that, so before getting into the details of the signal processing, so these 4 signals, where are we using them? So first signal is the analog signal. So the analog signal, which is continuous in time and continuous in amplitude, the real world signal which is acquired through a device or a sensor. So this signal is passed through the analog to digital converter. So analog to digital converter gives the digital signal. So digital signal is something which is one of the categories we have seen, but still it is different from the 4 categories we had seen. So the digital signal is only ones and zeros. So these ones and zeros are passed to the DSP or FPGA for processing, where we are looking for processing the signal ECG, interference removal, or baseline wander, or the speech signal noise removal. We can say the seismic signal noise removal. So these algorithms, it can be for 1D signal, or if you take a 2D signal, that 2D which is corrupted by a noise, that in the image which is corrupted by a noise, it is having the more flash in your image. So these type of processing, either it is 1-dimensional or 2-dimensional, we restrict our ideas, the algorithms, to 1D, maximum to video signal, that is 3D. So all these algorithms are put in the DSP digital signal processors or field programmable gate arrays. This is the digital wherein the digital signal is processed. After processing this, the digital signal or the signal which is corrupted with a noise or filter or just an amplification or any of this, and then the digital signal is out from the FPGA or DSP. These are also zeros and ones, and these zeros and ones are again given to a digital to analog converter, and this digital to analog converter gives the output as analog signal. So, which is the real world analog. So, this signal is after processing the input signal. So, it is not same as that. So, what the process we want to do, that is done in the DSP or FPGA and then get back to the real world. So, what are these ADC and DACs having? So, because it would be 1D signal, if you want to process, you have to capture that signal and pass it, make it digitized and then give it to the DSP. So, here if we take this ADC, so totally what are the functions it does? So, where do we get these 4 categories of the previous things signals types we discussed? So, analog signals, this is going to be a continuous in time, continuous in amplitude. As we sample it, the sampling theorem and other things we will be dealing with it in detail. So, the sampling does the job of just chopping the signal at a regular interval. Here we are using the uniform sampling, it is not a random sampling. So, uniform sampling identify this input signal maximum frequency or the bandwidth, and then fix the sampling frequency at least twice the maximum frequency. So, after this sampling, so we get the signal, you can notice that it is discrete in time and continuous in amplitude. So, discrete in time, that means it is defined only at certain interval of time, but still it is continuous in amplitude. So, discrete in time and continuous in amplitude, this is another category, you get it through the sampling. So, after DTCA you got, then make the quantization, that means rounding off, need to the nearest value. So, the quantization produces the discrete in time and discrete in amplitude here. So, the time is again integer values and amplitude is also taking the integer values. So, you got the 3 categories over in the ADC only, and then what we got the values of discrete in amplitude. So, those values are passed through the encoder, or it can be a 4-bit encoder, 5-bit encoder or any of this, and make or 3-bit encoder, depends on the amplitude of the signal, and make ones and zeros. So, these are all, suppose it is the input, the value here is suppose 5 and make it 101, or it is 4 100. So, this digital signal, so it is slightly different from these 3 categories in the meaning that it is only ones and zeros. So, these ones and zeros are passed to the DSP here now. So, this is passed to the DSP and then processed, your design or the filter or in 1D or 2D is getting into this device DSP or FPGA, and after processing again you will get the output as ones and zeros. So, the signal, the noise removed signal here, getting that ones and zeros. Suppose the objective is to just remove the noise, the digital signal. And what does it do, this digital to analog converter? So, here the ones and zeros what we got after processing is getting into the decoder, because you have encoded here, making it ones and zeros, and make this zeros and ones, what is it to the real world, we need to understand. So, that zeros and ones are again changed to discrete in time and discrete in amplitude. That means you are keeping that 0 1 0 1 the 5 value for one sample, and then this is made, this discrete in time and discrete in amplitude is passed through the reconstruction device or the operation. Here reconstruction will have a certain algorithms or the operations which can make this discrete time and discrete in amplitude to continuous in here we have this amplitude would be continuous in amplitude, but this will be dt only, discrete in time only. So, the output would be here again the discrete in time and continuous amplitudes. The 4th category which I had shown in the previous slide would be this one would be the output of this after reconstruction. Okay, so it will hold a sample and hold circuit, or first order hold, second order hold, or 0 order hold. Any of these reconstruction filters can be used to get this back again. So, this real world we have come back, the process signal is again now used for further usage here. So we can see the 4 categories of the signals in this process, mainly CTCA, DTCA and DTDA, where digital signal is something different from this DTDA. This is digital. When we say digital, it is ones and zeros. And then digital is passed through decoding and then get the discrete in time and discrete in amplitude. This is the fourth category where in digital to analog converters we use it. And then the reconstruction filter to get the analog back here. So here the amplitudes will be continuous here. So this gives the four categories of the signal. So further, when we talk about the signals can be again classified, that depends on the properties it possesses. So we take this as one case as continuous and discrete time, depends on the time, and the amplitudes we made it the signal classification like the before, the one which we had discussed. And the second one is analog and digital signal. So CTCA, and this is zeros and ones. So it can be when depends on the pattern, the function. It is depending on the time variable, right? The 1D signal. So that 1D signal, is it any repetition in the pattern? So when we say speech signal, that is aperiodic, but I said some pattern will be repeating, that is quasi-periodic. So whether it is periodic or aperiodic, so is there any pattern repeating in the amplitude of when it is a function of time? So this depends on that we can classify this periodic and aperiodic. So that why do we classify this actually? So if we classify this, we can use a particular signal processing algorithm which is meant for this type of signals, so that the processing would be easier. So and then even and odd signal, the signal is even or depends on the symmetry, whether the signal is even or odd signal. And it can be that energy signal or power signal. Mostly it is periodic, or that the signal is aperiodic. So it depends on it contains an energy or it is having the power. The root mean square values of this can be found also using some of the methods. So these are classification of the signals. So apart from that, is a signal is deterministic. That means can you express that in as a mathematical model? And do you know it is probabilistic, like that is random in nature. So you cannot express it in a particular way with using the mathematical equations. So then it is going to be a random signal. So we can classify them, and we'll see one by one these type of signals in the first few lectures of this course, and then we'll move on to the two-dimensional signal processing. So the case of analog, this is known now, time is continuous and discrete in the time. That is also two things, and analog digital also. Periodic and aperiodic, I will take it up in this lecture, and then we'll see even and odd signals as well. So the energy and power, and then deterministic or probabilistic signals. So the first one is even and odd signals. So if we take the even and odd signals, so would like to give this both of them, that is like continuous in time and then discrete in time. So continuous time and discrete time signals what is the even and odd expression? How do we get it? What's that even and odd means here? So if we take the signal x of t, which is continuous time signal, okay, so it can have two parts, that is even part and then odd part. So you can sum it up with the even part and odd part, or segregate this x of t and even and odd signal, that is even component of it or the odd component of it. So and then the even signal, when we say, what does it mean? So the x of t is equal to x of minus t. That means if you take the negative time of the minus t, the amplitude is same as x of t equal to x of minus t, and if the x of t is minus x of minus t, that means it is a negative of it. The x of t, whatever the time when t is greater than 0, suppose it is positive, and for t less than 0, it is negative of same amplitude, then that is an odd signal. So even signal or odd signal, we are not going to the further symmetricity of it, just to understand the basics of what is the even symmetry and this is odd symmetry. So with respect to t equal to 0, so we can say that this x of t equal to x of minus t and x of t equal to x of minus t. So in this, how do we get this even component from an x of t? So this even component is taken, if you know the x of t, and flip it x of minus t, take the t to x of minus t, and add them both and take the division by 2. So 1 by 2 x of t plus x of minus t would give the even component of a particular signal. If signal x of t is known, you can easily extract the even part of it from the signal. And odd part, similarly, if you have if you know x of t and minus sign, which gives in the same expression the odd signal, x of odd equal to 1 by 2 x of t minus x of minus t. Okay. So this for a signal which you have x of t, even and odd component can be obtained. So this for a discrete case, similarly this discussion can be extended to x of n. So where n is an integer here, it is that like in continuous time, it is not defined in all instant of time. This is only defined in a particular instance of n. So x of n equal to x of even plus odd. We can have them as two components a signal x of n contains, and if for even signal x of n is equal to x of minus n, so that is the amplitude is same for the negative index also, and positive index, whereas for odd signal the amplitude is not same, it is going to be a negative of each other. So for the even component, similarly we will like the continuous time signal x even n equal to 1 by 2 x of n plus x of minus n. So if you know x of n, we can take out the x of even component by flipping the signal x of minus n and adding them 2 and get it divided by 2. So the odd component of the signal similarly can be obtained, x of odd equal to 1 by 2 and x of n minus x of minus n by 2 would give the odd component. So you can take a even and odd component from x of n, the known signal. So we can separate it. If x of n contains both even and odd, then you would get these two components from it. So even and odd functions, to visualize it, just to visualize, you can see that there is the time in t here and x of t. So it's x of t is function of t, and there is a point a marked over here, a and minus a. So x of t equal to x of minus t. So that is what is mentioned. This is the even function here. And if you take the odd function, similarly the t and x of t, where the a marked over here, if you take at the same instant of time in this negative t, that is going to be minus a. So the amplitude is negative. So this is an odd function. This is with respect to the t equal to 0. This is with respect to t equal to 0 again. So this is continuous in time. Suppose we take x of t, a signal e power minus at. Okay, so this is an exponentially decaying function. It's a function of time. As t increases, goes to infinity, this becomes 0. So x of t e power minus at, in which if you want to take out only the even component of this signal. So how does it look like? X of t and x of minus t. So flip this signal x of minus at. Okay, so this is my x e power minus at, and that is going to be how do we take the flipped one and add them to x of t plus x of minus t. So this is 1 half e power minus at, and this is plus half here e power at. So these two, the flipping sequence comes over here. This is the flipped sequence, and this is this sequence, and divided by 2 make the magnitude half. This is 1 here, and this makes this half. Okay, so this is x of t signal, and this is x of minus t. That is a flipped signal, and add 2 of them and then make 1 by 2. So similarly, odd component x of t, this signal, and flip it as we did in this case, flip the sequence here, and then subtract one from the other, that is a flipped sequence from the original x of t, and divide by 2. So what we get is this x of e power minus at, and here is minus of minus e power at. So you can see the half and minus half. So this is the odd sequence. This is obeying that odd symmetry property with respect to t. This is positive and here it is negative. And for the even signal, similarly these two amplitudes are same when t is negative, one side positive and the other side negative. So this is getting the even and odd component from a x of t. And we come to the next category of this, periodic and aperiodic signal. So the periodicity, when we say and or aperiodicity, how do we define it? So because we are going to deal with many of them, the digital or the discrete signals, so we will first take the periodicity for the discrete time signal. So for the discrete time signal, that means time of this is defined only in integers. What is the equation, or what is the condition for this, what is the definition for this periodicity. So if you take this x of n, so x of n is the signal which is discretized, okay, so, and then that should be equal to x of n plus capital N. Notice this n for the n is a positive integer here, okay, it's a positive integer, and this n, this equation should be valid for all integer of n. So where is what is the n value for which this is valid, x of n equal to x of n plus n. So the smallest integer, also this should be a smallest integer for which this expression is valid, it's called the fundamental period. So the n which is satisfying this equation is called the fundamental period. So this signal in x of n, you can see a regular pattern repeating. What is the number of sample in which this pattern is repeating? So that's what we are trying to say, that if the pattern is repeating, and then this is going to be a periodic. If there is no pattern, or then no repetition of the patterns, or the amplitude which with respect to time is not repeating, then it's going to be then aperiodic sequence. So if we will see, and moreover, if it is a angular frequency that omega is related to 2 pi by n, that n is a fundamental period here. So if we take the signal, suppose cos omega n, to apply the x of n equal to x of n plus n. So this is x of n, and what we have, this cos of omega, n is replaced with n plus capital N. So what is the n value for which this is satisfied? Okay, so we need to find that. So we can multiply this omega n and omega capital N. So what is the value in which this cos omega n left hand side would be equal to the right hand side? So what is the condition on this omega n? So this omega n is when we have this 2 pi m, so where m is an integer, then this equation x of n will be equal to x of n plus n. So what is the ratio of m by n, that is m by n for this? The 2 pi, this omega by 2 pi, if you take omega by 2 pi, that is equal to m by n ratio. This ratio should be a rational number, okay, that is m and n should be an integer here. So that's the condition for periodicity. So cos omega n is periodic, okay, only if omega by 2 pi, this is going to be a rational number, okay, so that it will have a ratio of integers m by n. So what we had seen so far in this course, as a first introduction of this signal, what is signal, and then what is one dimensional signal and the 2-dimensional or n-dimensional signal, and the images, and how does it have the intensity if it is going to be a 2D image, and what is the intensity, how does it is a function, it is going to be a function of x and y, and the case of video, what is the 3D signal, and what are the classifications we can have, broad classification like continuous in time and discrete in time, and subcategories. Also, how can we broadly classify these signals like even and odd signal, periodic and aperiodic signal, also the energy and power, and deterministic and probabilistic signals, and so on. So we have seen only the two cases, even and odd and periodic and aperiodic. We'll further explore about the periodic and aperiodic signal, as well as the even and odd and the power and energy signals in the next lecture. Thank you.